Welcome to CIE Math Homework. We want to take a look at this further mechanics paper from May, June 2021. I hope you enjoy it. So this first question is for us to figure out an expression that relates the velocity of a particle that is in motion and experiencing a resistive force of this given magnitude. The net force acting on this body in the direction of motion that we're going to call MA is equal to the forces that would have been in the direction of motion, which there is none, minus those that are against the direction of motion. So we have this. Good. Now the acceleration we are going to rewrite as the rate of change of velocity with time. And since the mass of this body is just 1, I'm going to go ahead and write the acceleration on the left hand side as. This equation as we have it is a separable differential equation. So we're going to go ahead and separate the variables and proceed with the solution. Great. So now that we have this equation, we're going to go ahead and do some pre-processing and move ahead with solving this differential equation for the value or an expression involving v t. Now we go ahead and integrate both sides of this equation with respect to the respective variables that we have. Now this is a good point to use a given initial conditions. So at t equals 0, v equals 25. Great. So this left hand side just becomes 25 raised to the power half, which is 5 times 2. That will give us 10. And the right hand side as well, we have 10 plus c. And 30c is equal to 0. So we'll rewrite this equation or a relation between v and t as. At this point, we can still polish this up a little bit and have v in terms of t as. Now we just found this by squaring both sides of this final equation, and that gives us v equals 25 divided by t plus 1 all squared. And as you can see, at t equals 0, v equals 25. Okay, so for this second question, we have a body or a particle p of mass m moving in a horizontal circle on the inner surface of a hemispherical ball. So just look at the lower half of this circle we have, which represents our sphere. Great. And the distance from here all the way down here is what we are calling x, because that's how far up the horizontal circle is from the lowest point of the circle. This distance from the center to a point of circumference is the radius a of the hemispherical ball that we have. Now let's call this angle here alpha. If that is true, if this body is moving on the inner surface of this hemisphere, its weight, of course, acts vertically downward. And there should be a reaction from the surface. I'm going to call that R. And the vertical component of R, which is going to be R times sine of the angle alpha, should be equal to mg. And the x component or the horizontal component of this R is what will provide the centripetal force that will keep this body in the horizontal circle. This should be equal to mv squared over the radius of the circular path. Let me call that small r for now. The radius of the circular path should be the distance from this place all the way up to here. This is the radius of the circular path. And we can relate that to the a that we know as. Great. So let's call this 1. But before we call this 2, let's rewrite that equation. Multiplying 3 by cos alpha, we have and dividing 3 by a, we have now let's call this 2. Now solving 1 and 2 simultaneously, I'd like to divide 2 by 1 and have Now on the left hand side, I like to rewrite this as and multiplying 3 by 3, I would have now using the quadratic formula. This gives us sine of alpha to be equal to either 1 over 3 or sine of alpha equals -3. And of course, sine of a value, a real value of alpha cannot be greater than 1 or less than -1. So go with sine of alpha equals 1 over 3. Now let's try and figure out what the value of x should be. Remember, the distance from the center all the way down here should be a. And the distance from the top here all the way up to where the horizontal circle starts should be a times sine of alpha. That is what we have here. So we can conveniently say that a, which is the whole length of the line from here all the way down here, should be equal to a times sine alpha plus x. So the whole of this distance, which is a, should be equal to this, which is a sine of this angle plus x. So since we want x in terms of a, we are going to rewrite this as x is equal to a minus a sine alpha. This should give us a to 1 minus sine alpha, and that gives us x equals 2 over 3a. So that's it. Question 3 is in 2 parts, so let's take the first part. One end of a light elastic string of natural length a and modulus of elasticity kmg is attached to a fixed point a, so let's graph this one. The other end of the string is attached to a particle p, so let this be a particle. The particle p hangs in equilibrium at a distance x below the level of a. So let this be the natural length of the string, and this is some extension I'm going to call e for now. And we've been told that the whole of the distance where p hangs is x from the point A. Now we want to show that the value of k, which is part of the expression of the modulus of elasticity of the string, should be 4a divided by x minus a. So let's see how that goes. Since p hangs in equilibrium, the tension in the string should be equal to the weight of p, which is 4 mg. Where it hangs in equilibrium, the net force acting on it should be 0. Now the tension in an elastic string should be equal to the modulus of elasticity we are going to call lambda, multiplied by the extension, everything divided by the natural length. That means we have great. Now we have mg on this side, mg on that side. We can simplify this equation as hence we can make k the subject, and that is the expression we are looking for. Remember, x, the whole of x minus a is that extension. So lambda times the extension over L, that's what brought us to the expression we have here. So we have shown that k is equal to 4a divided by x minus a. Now we have a particle of mass 2m attached to p. You know, p already has a mass of 4m. So now that we have added a 2m mass to p, the total mass is going to be 6m, making the weight to be 6 mg. The combined particle is released from rest at the original equilibrium position of P, which is the point I am indicating. And when the particle descends a distance of 1/3a, its speed at that point, we're going to call that u to be equal to 1/3 root of a times g. That's the speed we have as at a point 1/3 of a down. The next thing we want to look at is the value of x in terms of a. So we want to figure out how is x related to a. So let's get started. Now it's crucial you know that we need to use the energy method because it is easier to analyze the motion of this particle. Let's start by calculating the change in gravitational potential energy from the starting point, which is this level, to where we are going. So this is level 1 and this is level 2, change in gravitational potential energy. That should be equal to the mass of the combined particle times acceleration due to gravity times the change in height. For the change in height, since I'm going from a high level potential to a lower level of potential, I'm going to call that change in height to be negative. So this one is 1/3 times a. And if we're moving from a lower potential to a high potential, I'd have made it positive. Great. In essence, the particle would lose some of its gravitational potential energy by moving from a higher level to a. We can simplify this as -2 times amg. Now let's also look at the change in kinetic energy that takes place from this point 1 to point 2. This is going to be half the mass of the combined particle multiplied by the change in the square of the velocities. So this is going to be now let's simplify this as well. The last thing we want to look at here is to look at the change in elastic potential energy. It would be great if we look at the changes critically so that we don't make any mistakes with the elastic potential energy. So I want to take it one step at a time. Let's look at the elastic potential energy at the point 1. So I'll call that EPE1. So 4a over x minus a is a k, and the lambda is kmg. So this kmg multiplied by x squared. X here should be the extension at the point 1, and that extension will be the expression x minus a, all divided by 2 times the natural length of our string. Let's simplify this. So this 2 divides us 4 twice, so we have that. And this a divides us a, and mg we have x minus a squared would simplify to just x minus a when we divide by x minus a. So this is the elastic potential energy at the point 1. Let's calculate the elastic potential energy at the point 2. Before a over x minus a mg, which is lambda, the extension in this case will be the whole of x minus a plus this extra extension, which is 1/3a squared. We're going to divide that by 2a. So lambda x squared over 2 times the original length. Let's simplify this as well. This 2 divides that, the A divides that as well. We end up with this is a good point to find the change in elastic potential energy. So the change is the final value minus the initial value. So I'm going to write this as, and I'm going to try and factor out x minus a. I have a big bracket. Great. This simplifies to you can further simplify this bracket and have the x squared and the x squared will go away, and negative 4 over 3 minus negative 2 give us 2 over 3. Then the 4 over 9a squared minus a squared give us. Now at this point, it's now ideal to use the conservation of energy principle since there are no external forces acting on a particle. So negative 2 amg plus 1 over 3 amg plus 2 mg over x minus a multiplying. So I want to factor out the a from this bracket and just have 2 over 3x minus 5 a. This is equal to 0. Clearly we can simplify this as now we can cancel out amg on both sides of this equation, and then that will leave us with now let's expand the brackets and simplify. Now let us group like terms and solve for x in terms of a as we need to. So x is equal to 5 over 3 times a. And this is the relationship between x and a as requested. Great. So for this fourth question, we are supposed to find the center of mass of the combined solid we have to the far left, the cone combined with the cylinder. Great. So on the far left, we have the shape. We have the mass of that shape, the center of mass, the reference point that we given, which is the base of the cylinder. So let's consider the. Since the two bodies together, we are going to consider to be uniform. That means the mass is uniformly distributed over the entire volume. So given the mass per unit volume to be ruled, we are going to calculate the mass as. So pi r squared, the height of the cone, which is the volume of the cone, multiplied by the mass per unit volume. That should give us a mass. Now its center of mass, get to that in a bit. Now let's talk about the cylinder. Again, the volume of the cylinder is pi r squared h. Multiply that by the mass per unit length. that gives us the mass of the cylinder. Now the mass of the combined solid, that should be the sum of these two masses. So I'm going to factor out the factor and then have the sum. So pi r squared h is common to these two terms. With the cone, I'm left with third of k, and with the cylinder, I have just one. Now, the center of mass of the whole system, that's what we are looking for. Let's use this variable to represent y bar. That of the cylinder, referring to the base of the cylinder, is halfway along the so yeah. And that of the cone, according to your MF19, is supposed to be a quarter along the height from the base, or 3/4 from the apex. So from the base, a quarter of the height. I'm going to add that to the height here to give us a center of mass's location from the reference point we have. So that should be a quarter of hk plus h. So when I factor h out, I have a quarter of k plus 1. Great. Now let's go ahead and take a moment about this point. Now the product of the mass and the center of mass plus that of this mass times the center of mass should give us the total mass times the center of mass of the combined solid. And that would mean that now let's simplify the expression for y bar. Great. Now let's simplify this further. Pi r squared, one of these h's together with rho will go out with this. And that leaves us with just h in the numerator outside the brackets. With what we have, it will be a good idea if we remove the fractions by multiplying through the top and the bottom by a common factor, let's say 12. This 12 multiplies through the numerator and gives us 6 as the far end. And 12 together with 1/3 will give us 4. That 4 times this first term give us just k squared. And the 4 times this give us just 4k, the numerator. Remember, there's h outside of the bracket. And to divide that by multiplying through the down 2 by 12, and that reduces the 1/3 to 4k, and 1 here becomes 12. So this is as simple as required. So the center of mass is y bar away from the base of the cylinder. Great. Now for the second part of this problem, now our solid is placed on a plane. So let me draw that plane. And we are told the plane makes an angle of theta where tan of theta is 4/3. Now if this is the center of mass of our solid, for this whole thing to be at the point of top plane, the line of action of the weight should be passing through the edge. So the weight should be acting, of course, passing through the center of mass and also at the edge. This is what needs to be satisfied for this body to be at the point of top. Great. And if that's the case, perpendicular line from the center of mass to the base would be y bar from the base. The distance from here all the way down here will be y bar, and if that's perpendicular. And from here all the way down here we r. Remember, if this angle is theta as we are saying, the angle up here will be the complement of theta. This angle will be vertically opposite to that complement, and if there's a 90-degree angle, this has to be theta. Great. So this is the center of mass of the solid, and the vertical or the line of action of the weight makes an angle of theta with the line that is perpendicular to the base of the cylinder. You just take the tan of this angle, this triangle, would have, and that will imply that tan of theta, which is 4/3, is equal to r times the inverse of y bar. So y bar is h into k squared plus 4k plus 6, all divided by 4 times 3 plus k. The inverse of that would be, now remember in this expression we have r over h, and here we have a condition that relates h and r. So if you want to find r over h, that will be 3 divided by 2. So using that here, 4/3 should be equal to the r over h, which we now know as 3/2 multiplying 4 times 3 plus k over k squared plus 4k plus 6. Let's simplify this expression, and it's of course going to be a quadratic in k, and we can solve that easily. This 4 can divide this 4, so on the left, all we have is using the quadratic formula, k is equal to, now from what we've done, k would be either 3, -5, 2. Remember, the height of our cone cannot be negative, so go with k is equal to 3. So the value of k with k equals 3. And that solves the second part of the question. Now for this fifth question, there's a lot of information here, but it's not a difficult question. We're going to do that quickly. Now let me represent the path of the particle P, which is a vertical circle, by a circle. Great, so we have this circle, and the particle P, whose mass is m, is attached to one end of a light in an inextensible string of length. I mean, the distance from the center to where the particle P would be is a. The points A and B are all on the path of E, and they are all on the same side of the vertical through. So if there's a point O and there's a vertical through, the points A and B are on the same side of that vertical. Let's put it on the right, put it on the left, but both of them are on the same side. We're told that OA makes an angle of theta with a downward vertical. So if this is O and this is A, there is this acute angle theta with a downward vertical. Now OB, on the other hand, makes an angle of theta with an upward vertical through. This is what it implies. The two angles are the same, just theta. Now the speed of P when it's at A is u. So I'm just going to say V equals u at this point, and say V equals root of Aj at this point. Now we have some relationship between the tension in the string at A and then at B. Let's see how that helps us. Our work here is to find the value of theta and an expression for u in terms of A and J. Let's begin by calculating the value of the tension in the string at the 2 points A and B. Great. At the point A, the weight of the particle P would have been acting down vertically. So I'm using this dotted line to represent that. Now, if we extend the line of action of the tension in this string, it would go down this way. And then this is the line perpendicular to that. So this is just an extension of the line of action of the tension in this string. And then this line is perpendicular to that. Now, the weight, of course, acts vertically downward. There's a component of this weight that is acting along radially from O to A. So that is acting this way. And of course, there's another component that is acting here in this direction. These two together, these two components, the vector sum of these two forces or these two quantities gives us the total weight acting downward. I'm going to call that weight mg. But there's the weight, so it's acting vertically downwards. And this is just an extension of this line. That means the angle theta is the same as this angle. Now, if you should do mg cos of this angle, that will give you the component of the weight acting along this line. I'm going to write that here. And that is all we need. We need the forces that are acting radially from O to A so that we can tell what forces together are contributing to the centripetal force, keeping the particle P in the circular path about O. Now let's look at what happens at the point B, because we need that as well to figure out the tension in the string. Remember, if there's a particle, the tension in the string on P is acting toward the center. The same thing happens at this point. At this point as well, the weight of the particle P acts vertically downward. There's a component of that weight acting toward the center of the circle, and there's another component acting perpendicular to that. So the two together, this together with that, the vector sum should give us the total weight which is acting vertically downwards. This line is parallel to this vertical, so this angle and that are alternate angles, and they should be. That will mean the weight mg times the cosine of this angle should be the component of the weight acting along the rope from B towards A, radially towards the center of the circle. Now, the reason we are doing this is for us to be able to apply Newton's law at the 2 points. So let's start with the point B. At the point B, the tension in the string we are calling TB is acting toward the center of the circle. The component of the weight at that point is also acting toward the center of the circle. The two together are contributing to the centripetal force that keeps the body P in the circular path at the point B. So we would have good. So this is m times the square of the velocity divided by the radius, and this is centripetal force. We can polish this up and have now at the point A, let's see what is happening. The tension in the string is acting toward the center of the circle. But the component of the weight acting radially is away from the center of the circle, so we have that. And these two, the sum, as we have it, is the net force acting toward the center of the circle. That should be responsible for the centripetal effect. Now let's polish this up as well and continue. Now we've been presented with a relationship between TA and TB. So right away, I'm just going to go ahead and write this is TB. So multiplying that by 7 should give us so far we've come up with a relationship between U and agent, but that involves cos of theta. So go ahead and see what else we can do to get another equation that will help us to eliminate theta, find the value of cosine theta, and continue what we have to do. Now let's consider energy change between the point A and the point B. So from A to B. Or you can do from B to A, but however you do it, it's up to you. So I'm doing from A to B. Let's start with kinetic energy change. So the change in kinetic energy will be the kinetic energy at the final position minus the kinetic energy at the initial position. And that will be now let's look at the change in gravitational potential energy. With that, we need to look at the vertical displacement from the point A all the way to the point B. So let's do that. Remember, from here up to this point, from the point O to the point A, is the radius of the circular path we are going to A, small letter A. If this angle is theta, this is also theta. The distance from here all the way down here is A cos theta. And since from here to here, the same as from here all the way up to B, the vertical displacement is just 2A cos of theta. And remember, I'm moving from the lower point to a higher point, so the change in gravitational potential energy is going to be a positive change on E. Now we look at energy conservation, where so we have at this point the m here and this m here will go away. Would have now this is another equation involving u squared and everything else. So now since the u squared is just the square of the velocity at the point A, the two expressions should be equal. Now we can just group like terms and simplify the equation and solve for cos of theta. Remember, there's AG running through the entire equation. We can just simplify this too. So now we have found a value for cos of theta, and that is half. And that is all we need at this point. Now that we have a value for cos of theta, we can go ahead and substitute this value of cos of theta into any of the equations involving u, so that we have so we can just take the square root of both sides. Since u is speed, we just take the positive square root of that. So this is how A, J, and U are related. So with our last but one question, question 6, we have two spheres, two uniform smooth spheres, A and B, same radius, same mass. They're both moving with the speed u, but in different directions. They have the coefficient of restitution given as 1/3. Along the line of centers, what speed is B approaching A with? What component of this u is propelling B forward? And what component of this u is propelling A forward? To know this is very crucial. Now, if u is acting at an angle beta to the line of centers, then u times cosine of beta is this component, and this is u sine of beta. On this front, times cosine of alpha is acting towards E, where sine of alpha acting upward. So these are the speeds before the collision. Now these speeds are related. Before we go ahead, let's take to be the speed of B along the line of centers after the collision. And let's take AA to be the speed of A along the line of centers after the collision as well. Taking this direction as positive and using the principle of conservation of momentum, we can say that and we can simplify this to have and with a given relationship between cos of alpha and cos of beta, we can say that now let's use Newton's law of restitution, and according to that, the coefficient of restitution, which is 1/3, should be equal to the relative velocity of separation, which I'm going to call VB minus VA, because VB is acting this way, VA is going this way. The relative velocity will be this minus that. But this has to be positive and divided by the approach. So we can simplify this further in half. Now let's further simplify this final equation that we have and still make use of this relationship that we have. Let's call this 2. Now solving these two equations simultaneously, we can add them and that will eliminate BA. And on the right we have 2BB. On the left we have 2U cos beta. And if VB is equal to U cos beta, putting that into any of these two equations give us VA 0. Now take a critical look at something. If after the collision, the velocity of A along the line of centers becomes 0, but A maintains its velocity in the forward direction, that will mean that, or hence, it shows that the direction of motion of A after the collision is perpendicular to the line of centers. In other words, the component of the velocity perpendicular to the line of centers is 2 sine alpha, but the component parallel to the line of centers after the collision becomes 0. So A now moves with this velocity or this speed, and clearly it is perpendicular to the line of centers. So we have shown that by showing that VA equals 0 and the argument I made, A moves in a direction perpendicular to the lines of centers right after the collision. Now we've been told that the total kinetic energy of the spheres after the collision is 60 over 4 mu squared, and we now have to find the value alpha. Now let's see how to solve that. After the collision, the speed of B along the line of centers is this, but perpendicular to the line of centers is still that. And the speed of A along the line of centers becomes 0, but perpendicular to the line of centers becomes we have. That will mean that the total speed of A, so the speed of A is going to be 2 sine alpha, but speed of B in total, using Pythagoras theorem, B. And this simplifies to if that is the case, the total kinetic energy will be the kinetic energy of A plus that of B. That should be equal to, now there's U square running through, there is M running through, so that's, and we can even multiply 2 by 4 to clear all fractions and have a simpler equation that looks like this. Now, looking at the angle alpha, it's an acute angle, so the sine of it just has to be positive 2 over 2. So that's how come I'll select sine alpha to be that. If this is true, then alpha is sine inverse of root 2 over 2, which is 45 degrees, or pi over 4 radians. So we have a particle P undergoing a projectile motion from point O on the horizontal plane and moves under gravity. The initial velocity of P were given to 100 meters per second, and tan of the initial angle of projection is 4 over 3. Now, the two times at which P's height above the plane is h differ by 10 seconds. The particle P at any point along its flight vertically, it will be at a given height twice. One time on its way up, the other time on its way down. However, at the highest point, it will be or it will reach there just once, or at only one point in time. So if you can tell how long P takes to get to the maximum height, then the 2 times that P has been at a point H should be evenly spread around that time for the maximum height. This is what I mean. Consider a horizontal line or parallel to the x-axis. P reaches this point H on its way up, and on its descent also passes through that point on its way down. So it reaches the point H twice. First time on its way up, the second time on its way down. The midpoint here is how long it takes for P to reach the maximum height. That is, if you are plotting a graph of displacement of P against time. But this graph I have here is actually the equation of the trajectory, which is the y against x. Good. Now let's see how long it takes P to reach the maximum height. The velocity of P along the y-axis at any point in time is given as, and given that tan of theta is 4/3, then sine of theta should be equal to 4/5, and cosine of theta should be equal to 3/5. And in that case, we can rewrite our velocity along y as now at the maximum height, the velocity along y is 0. You can find t as and this simplifies to. So it takes 8 seconds from the time of projection for the particle P to reach the maximum height. If that is so, the time that the particle reaches the height h before reaching the maximum height, it should take 5 seconds, and after reaching the maximum height, it should take another 5 seconds. Remember, the graph is symmetrical about a given point. So if that point is the maximum point that we have just found, then before it, 5 seconds, after it, 5 seconds. And that implies that we got to the height h at time 8 minus 5 seconds and 8 plus 5 seconds. The first time is 3 seconds, the next is 13 seconds. So now let's find the value of h. Displacement along the y-axis given us and that is equal to now when we simplify this, h to be 195 meters. Another way we can look at this same problem is to say that let t be how long it took to get to the height h on the way up. Alright? So that h should be equal to 2t sine theta minus half gt squared. Remember, we'll reach the point h again after 10 seconds. 10 seconds after t, the original t seconds. That would mean that the same h now let's simplify the second equation and then solve the two equations simultaneously. we have that. Now, since the two h's are the same, you can equate the two, simplify, and solve for t. And when we know what the value of t is, substitute that back into any two equations, the value. Of this negative 5t squared and this negative 5t squared go away. The 80t on the left and this 80t on the right will go away. End up with if t is equal to 3, substituting back t equals 3 into this first equation will give us h to be. Now the second part of this problem wants us to find the magnitude and direction of the velocity of E 1 second before it strikes the plane. So it would be a good idea to figure out when it strikes the plane and then 1 second before that, and then we can tell what. So for P to strike the plane, its vertical displacement should become 0. So the vertical displacement we are going to find should be equal to this should be equal to 0. Let's factorize this. So at t equals 0, the displacement was 0, that was at the point of projection. And at t equals 16 seconds, it should get to the ground again the second time. Remember, we want the velocity 1 second before it strikes the ground, and that would be at the time t equals 15 seconds. This is negative 70 meters per second. The velocity along x, of course, is just cos theta, and that is so the magnitude of the velocity. So this is 92.2 meters per second, correct with 3 significant figures. But this is just the magnitude of the velocity 1 second before it strikes the ground. Let's look at the direction of that velocity. So tan of alpha equals to tan inverse of 7 over 6 is approximately 49.4 degrees, correct to 1 decimal point. And this is below the x-axis, so we can state it as the direction is 49.4 degrees below the x-axis or below the horizontal. So that brings us to the end of this particular paper. I hope you enjoyed it. Like this video, share it, and subscribe to my channel. Thank you very much.